videos. Discussing distribution and factoring leads us automatically into the next most important topic in this particular area. We have to learn how to collect like terms. We have to define what a like term is. A like term is something you do like. However, it also means that they are alike. They must be exactly alike. When we see two different terms, 5x and negative 3x, we say, well, those can't be like terms because one's a positive and the other one's a negative. No, that's not how to judge like terms. Like terms have the same variable raised to the same power. The same variable raised to the same power. It doesn't matter whether the number is positive or negative. So in this instance, 5x, which all variables and all numbers always have a 1 even though it's invisible. We don't usually write it, we just leave it as x. And the term negative 3x to the 1, we see each one of them has an x to the first power. That means those are like terms. Like terms have to be exactly alike, with the letters and with the same power being raised to be like terms. So we have 3m squared, such a lovely number. And we have negative 13m squared. Those are like terms. With like terms, we need to have the variables and the powers to the exact same so that we can add and subtract. And this only is with addition and subtraction. Multiplication and division, you don't need like terms at all. But with addition and subtraction, they absolutely must be exactly alike. I can't overemphasize this because this is a common area where so many of us have made mistakes through the years in algebra, and we can correct that. If we have negative 36 e to the 54th and positive 89 e to the 54th, those are like terms. They are both the same thing. E to the 54th, e to the 54th is the clue. Not whether it's negative, not whether it's positive. Not whether this is a huge number or a small number, etc. No, that has nothing to do with like terms. I'm going to emphasize this because it's so important if we're going to add and subtract correctly. 3x and 7y, those are not like terms. X is not y. Y is not x. You cannot add or subtract those two terms together. Those are not like terms. Okay? 4y and 13z. Nope, they're not like terms. Can't do it. 19m squared n and negative 48m squared n, those are like terms. The m is squared here, the m is squared there, the n is by itself here, the n is single by itself there. M squared n and m squared n makes those both like terms. If this had been 19m n squared and negative 48m squared n, they would not be like terms, because the n is raised to the second power here. It's true they have the same variables, m and n, But n is the one that's raised to the second power here, while m is raised to the second power here. That means those are not the same. These are the same. These are not. So you'll want to be careful when you're doing these kind of equations. Sometimes you're gonna get something really hairy like qf squared dc cubed x to the sixth. And if you don't have a variable exactly like that raised to those powers, those won't be like terms. They have to be exactly alike. I cannot overemphasize that. We want like terms. Negative 16z cubed and negative 15z squared are not like terms. You cannot, remember, in adding, you cannot combine z cubed and z squared. You can if you're multiplying, but we're not talking about multiplying. Collecting like terms applies to addition and subtraction, and they must be exactly alike. You can have the same variable, z cubed and z squared, but they're not like terms. They both need to be z cubed if they're going to be like terms. When I say like terms, I mean exactly alike. I mean if it's a, then the other one has to be a. And if it's c to the 19th, then it has to be c to the 19th. If it's f to the negative 1, it cannot be f to the 1. Those are not like terms. It has to be exact match. Okay? I think I've destroyed my overemphasis on this, but the powers also must be the same. Not only the variable, but the powers have to be the same. Now let me show you how gathering like terms is done and how it helps us in solving problems, especially with addition and subtraction. Again, you don't have to worry about this with multiplication and division, just addition and subtraction. So there's a few differences with it. So let's do something fun. 1x and 2x. And you say, holy cow, I can feel that I have almost acquired my PhD in mathematics. Because I know that this equals 3x. Call me a genius. Well, you'd happen to be right, because these are the same variable, and they are to the same power. They have that invisible 1. So you're right, that's 3x. Make no mistake about that. Actually, what if we factor out the common term here? What's the common term here? X, isn't it? How about we factor out x? What are you left with? 1 and 2. Hey, isn't that cool how that works? We can factor this and still equal 3x, because this is x times 1 and 2 is 3. X third is 3x. Isn't that fun? That's cool. Okay, let's say we have x plus 2x. And you say, didn't we just do that one? Yes, we did. What I want to show you here is x plus 2x is 3x. And you say, dude, you just showed me that, with one difference. This one has a 1 in front of it. Most of the time, the problems will be in this shape, just x. We need to recognize that any variable has that invisible 1 in front of it. This is a 1x. If it was a plus 1, this is a 1a. And incidentally, you can't add those. Those are not like terms. This is 1a. This is just 1. This doesn't have a variable, so that is as simple as it can get, right? So this is important to understand. Now let's do something really difficult, one that will completely stump you. 8x plus 4x. You look at this and you say, okay, both have the variable, they're both raised to the same power. These are like terms. So how do you add like terms? You add the numerical coefficients. 8 plus 4 is 12x. You don't add the x's to x squared. You're not multiplying. You just keep the same variable. That's 12x. Let's say we have 3m squared and 5m squared. What does that equal? Well, you've got the like terms. If you pulled out the common factor, you'd see that this is m squared, and you'd be left with 3 plus 5. That's how to factor out that expression. M squared, 3 plus 5. This is m squared plus 8. 6n and 3m. When you see this, you say, well, all right, this could be 6 and 3 is 9 and m. No, not in addition. In multiplication, you could combine these, but not with addition or subtraction. The n is not an m, therefore the answer to this expression is 6n plus 3m. That is in its simplified form. That's the answer. You have to keep the unlike terms separate in your answer. If they're like terms, you can combine them, but you can't if they're unlike terms. You gotta keep them separate. Unlike terms, the interesting thing about like terms is the variables will equal real things in real life, like time and distance, speed, oranges, apples, etc. So it's important to know how to put together like terms. 13x squared minus 12x to the 5th. What do you think of that expression? Well, you have 13 minus 12 is going to be 1, and you have x squared and x to the 5th, but hold it. These are not like terms. Therefore, you cannot subtract them. So the answer to this is 13x squared minus 12x to the 5th. That is your answer. Like terms have to be exact. X to the second, x to the second. But this isn't x to the second, therefore it's unlike terms. That's how these work. We want them exactly alike. Now, if you have, let's say, 2x plus 3z and 4x, what does that equal? In this instance, and there's going to be times in equations where we really do get a whole conglomeration of mixed up numbers with variables, different kinds of variables. We want to collect the like terms together. Here's where your parentheses become your best friends. They will help you clarify and keep things straight. It's very important to do this now. Get used to this now, because when you get into an equation that has 59 terms, I promise you're going to get lost if you don't group things together. We have a common term, a like term with 2x and 4x. So put the like terms together in parenthesis, and then this plus 3z just comes along for the ride. Right? Now we can add the like terms. 2x and 4x is 6x. Very good. Plus 3z. And that is as simple as the answer can get because x is not z. So you pull your terms together, add them all together, and leave the unlike terms separate. Even if you have 55 different unlike terms, you have to keep them separate. Okay? And if you have 30 like terms, you must combine them using whatever operations it shows you to. Very most important. Okay, let's say we have 12a and we subtract 9b and we add 3a. It's the same principle here as we did here. We want to put the like terms together. In this case, 12a plus 3a. We want those together separated from the rest of them in our friends, the parenthesis, and then we subtract 9b. So 12a and 3a is 15a, and then we have a subtract 9b, and that is your answer. That is as simplified as this expression can get. We combined the two terms that were alike and added, and then we brought along the negative 9b because that is part of the answer. It just can't be combined anymore with the a. And that's how you answer that question. Very important to know this. Now what if you have 2/3 x plus 1/3 x? You say, well, we've got two fractions. Aren't those like terms? No, the fractions have nothing to do with being like terms. However, the x's do. We know each fraction has an x. Good. We know each fraction has an x raised to the same power, that invisible 1. Good. Those are like terms. So how do you add fractions? The first thing we need to check is the denominator. In addition, we have to have a common denominator. Well, we're in luck. These two have the common denominator already. So we simply add across with the numerators. 2 plus 1 is 3. We bring the same denominator across. So this is 3/3. This is 3/3 x. We have the variable. Well, everybody knows that 3/3 is simply 1. So this is 1x. We don't have to write the 1, so this is simply x. 2/3 x and 1/3 x is simply x because they were the like terms. That's how that works. Kind of nice. Holy cow, I've already gone through almost a half hour of videoing, and I have a whole ton more I want to show you. So I'm going to continue this in the next video, and what we're going to do is we're going to slowly build up the, we're going to have a whole bunch of different like and unlike terms so that we can continue practice doing this. This will save your bacon in physics problems. You really are going to have to know this if you're going into physics and engineering, I promise. So anyway, happy calculating. Have a great life. And come on back, man. I'll see you in the next video.